Okay, to understand why we're doing perfect squares, let's understand the vertex format. You'll often see it written like this, but all that h is trying to remind you of that negative h is that we make the opposite number, the negative version of it. And this k is just saying, yeah, it's whatever this is here. But that's very confusing. So it's always better to work with actual examples. In this case, we can see the vertex is in there like that. But the problem is, a lot of our graphs are represented in ax squared, this format, plus bx plus c. And in this case, it would be this. It would be x squared minus 10x plus 34. And if I turn this graph on and off, we can see it's the same as the red graph. That means this graph and this graph are the same thing. But what we're learning in completing the square is how to get from this to that. So first off, let's learn what a perfect square is. And this is very important as well. A perfect square is when you have the same factors multiplying each other. Those are the same factors. They're multiplying each other. It's going to create a perfect square. When I FOIL that out, it becomes x squared plus 3x plus 3x plus 9. The middle terms are twice. You see, we get the middle terms twice. 6x. So we can see that's the perfect square of that. This is also a perfect square, but negative times. It's a perfect square because both those factors are the same. This one becomes minus 4x, which is minus 8x, plus 16. But let's notice this pattern, because this pattern is important to notice and saves us a lot of time. Math is about learning a method and then improving on that method. Notice that it's always these first terms, whatever it is, squared, right there. And it's always these second terms, the 3, squared, right there. Notice that the x squared here is there, and the minus 4 squared is there. And then this middle term is always 2 times the first term, x, times the second term. Because there's 2 of them. Remember, there was always 2 of them. 2 times 3 is 6x. 2 times x here, 2x, times minus 4, minus 8x. If you want, you can do the 2 times the number first. 2 times minus 4, minus 8, times x, minus 8x. So we get this very useful pattern, which is written like this. If they're both positive factors, it's a squared plus 2ab plus b squared, which just means square the first term, square the second term, multiply the 2 of terms by 2 to get the middle term. The second one is in this format, a squared minus 2ab plus b squared. The reason it's always plus b squared because a negative squared becomes a positive. The minus 4 times itself becomes positive 16. So this is always positive, and this is always positive, but this middle term is negative if we're dealing with the negative 4 here, and it's positive if we're dealing with something like the plus 3 here. I also want you to note that sometimes they're going to give you trickier factors. And I want you to remember this formula there, because no matter what, the formula works. So you could have very difficult factors like this, 4x minus 2y, and just, we'll call it 2z instead of y. And so long as they're the same, that is still a perfect square. And it becomes 16x squared minus 8xz minus 8xz minus 16xz plus 4z squared. Squared. Just my typing will work. And not just making the black. There we go, like that. But notice it still works. 4x, if I say I take the first term and square it, is 16x squared. Minus 2z, if I square it, becomes plus 4xz squared. And 2 times minus 2 is minus 4 times 4 is minus 16xz. Oh, look at that, minus 16xz. 2 times the first term times the second term, and then we put a minus in there because there's a minus there. So it works no matter what. But notice that these are still perfect squares, even though it's no longer just x minus 2. It's got a little z in it. So when you're undoing a perfect square, you have to say, hey, is that got a square root? Does that have a square root? Is this 2 times the square root? So what would be the square root of this? If I work backwards, it would be 4x. What would be the square root of this? If I work backwards, it would be possibly 2 or minus 2z. And then I can say, well, what's 2 times this 4? It's 8. Times this 2, it's 16, xz. Is that 16 in there? Yes, it is. It's negative, though. So that tells me that this term minus this term. So if I can work backwards, too, if I can spot the pattern. So always ask yourself, is this got a square root? Is this got a square root? Is this 2 times the square root of that times the square root of that? If so, it's a perfect square. That's how you identify them backwards. Okay, but what's the point of that, Peter? What's that got to do with completing the square? Well, to get to the vertex format, we have to take this format, which is called the standard format of a quadratic, and we have to figure out how can we get to the vertex format. Keep in mind, we know the vertex right here is that. How do we work backwards to that? Well, the first thing you have to do is you look at the middle term. Well, actually, that's not fair. The first thing you have to do is say, okay, well, we're going to move the number aside and we're going to focus on the middle term. And remember from our exercise what the middle term was? I'm just going to copy this, by the way, and just move backwards and grab this as well. Grab what we had before, this part. I'm going to move it maybe way down like that. And then I'm going to bring this back. There we go. I'm going to bring this in. And just keep this in mind when we're working on completing the square. Remember, the middle term was 2 times a and b. And what's this middle term? It's minus 10. So now my second step after moving this number aside is to say, is there a number here? If there's not, we can skip step 2. And we'll discuss what step 2 would be if there is a number there later. My third step is look at this middle term, divide it by 2. Divide it by 2. That means the perfect square of x minus 10x is x minus 5 squared. And x minus 5 squared is the same as x minus 5 times x minus 5. So I can use this method over here to say, well, the middle term is always 2 times my terms. And say, okay, well, whatever this term is, I'm going to divide it by 2. And that's going to be my factor. It's going to be x minus 5 squared. Now I know that that's part of my vertex format. This is partially completed, and sure enough, I can see right up there, that's true. Right now, I have the x value of my vertex. It's the opposite of minus 5. And I want to show you a little cheat now. I want to show you a little cheat. And I've made a lot of mess here, so I'm going to go backwards. There we go. No, I like going where we had it. To there. The little cheat is, now that I know it's x minus 5 squared, I know my x value of my vertex is 5. I can go back to this original formula, put the 5 in where I see x. I get 25 there, minus 50 there, plus 34. I can add the like terms. 25 plus 34 is 58. Sorry, 59. So really I'm talking about 59 minus 50, which is 9. That means when x is 5, y is 9. Look at that. I can figure out the y value without doing completing the square. This is called partially completing the square. Simply because I divided that by 2, I now know my x value of my vertex, and I can go back and plug it in to figure out what my y value is when x is 5, and that will give me the vertex as well. That's a handy method to verify if you did it right. But now let's do completing the square. X minus 5 squared I know is going to be the completed square because minus 10 divided by 2 is minus 5. But x minus 5 times x minus 5 is what x minus 5 squared is. I get x squared minus 10, minus 5x minus 5x, which is minus 10x, which is what I want. I can see in the blue area, that's what I want. But it also creates this 25. And I don't really want that. I know I have a plus 34 over here, and you can say, well, you could steal 25 from that, but let's focus on what we do technically because it doesn't always work out smoothly with the 34. Since this 25 is nowhere in my formula, I don't want it. So by working, I can see this is the part I want, and I get it right there. But this, unfortunately, this squared, x minus 5 squared, creates this 25. And I don't want it because there's no 25 in my formula. Don't ignore the fact that I could technically get a 25 there. Which means I got to get rid of this 25 that's created when I make this x minus 5 squared. Sorry about chicken scratches. X minus 5 squared. That's going to create a 25 that's not here. So I have to subtract 25. To figure out what you subtract, you just find out what the square of this number is. Minus 5 squared is 25. I'm always subtracting whatever that is, number is squared. And then I add 34. Then I bring my number back. I say, well, I know that's 25 I don't want. So I have to subtract 25. And now I'm going to add my 34. Look at that. Minus 25 plus 34 is plus 9. That means this is the vertex format of this standard format here. If I were to expand this all, I'd get x squared. See, I'd get x squared minus 10x plus 25 and then plus 9. Plus 25 plus 9 plus 34. I got my standard form. So you see we're making a completed square in the vertex format that's the same as this formula, but we have to adjust for that number that we create when we manufacture our perfect square. And that's what we're doing. We're not only exercising our mind. The reason we use these graphs, and you might, why? That's the big question. Graphs are used endlessly to model reality. They're in engineering, they're in mathematics, they're in medicine, they're whatever. If I know something is going up steadily like that, I can predict the future of it. This is important because let's say temperature on the planet is going up. I can say, well, we're going to reach this temperature in 6 years if we're not careful. We have to change what we're doing if we don't want to reach this temperature, because this temperature is going to evaporate water and kill plant life and make our life tough and increase cancer and whatever. Increase energy resources, cause earthquakes, cause whatever. So being able to predict the future is a big part of how we have to adjust behavior. Sickness is the same. Not to harp on COVID, but since everybody went through it, it's easy to understand. They could see where the number of cases going into the hospital were, how many people were coming to the hospital. Therefore, they could predict how many people got infected 2 weeks ago. And therefore, they could predict how many people are going to get infected. And they would say, well, if this many people get infected, we don't have room in the hospitals. COVID wasn't dangerous in terms of the actual disease. COVID was dangerous in terms of its treatment. So if you did not have a hospital bed to treat the severe cases with a ventilator, or if you didn't have a ventilator, people were going to die that didn't have to die. That was the point. Our hospitals would have become overrun and we weren't ready for it. So we had to do a way to curb it. Well, disease is spread through contact. It's plain and simple. So all you say to people is, we have to keep people from contacting other people. So we're going to implement these isolation rules. Now, unfortunately, some countries did it well, and some countries didn't do it. In the USA, for instance, 5 times as many people died than in Canada. And in Canada, about 25 times more people died than in Australia. That's because in Australia, they had strict rules. They had police out on the street telling people to get inside. In Canada, we were semi-conscious, but about 20% of the people ignored it, were jerks, didn't care. And in the USA, they didn't care at all. So you could see from how many people died exactly the impact of the policies. Yeah, I'll stop harping about COVID. My point is not COVID. My point is they use graphs and prediction to figure out what's going to happen. A lot of the questions you're going to get in this course are going to be about finance. and they're going to use an upside down quadratic. Well, in finance, the vertex is going to represent your maximum profit because the y-axis will often measure profit. And the x-axis will represent how many units sold. So if I can sell an apple for $1 or 10 apples for $1, I'm going to make $10. But if I can sell 2 apples for $6, I'm going to make $12. Well, it's easier for me to sell 2 apples for $6. But the question is, will people pay $6 for an apple? And that's what finance is. How much will people pay? What's my maximum I can achieve? It's much easier for me to sell 2 apples for $6 than 10 apples for $1 because I have to store 10 apples. I got to get 10 customers. I got to do 10 transactions. This has negative effects in the United States, for instance, where they apply this to medicine and they charge $1,000 for a pill, let's say, because they know they're going to get sales. But not everybody in the States can afford $1,000. In Canada, we have a cap on our prescription drugs. But it's a good example of, in the USA, they run everything based on demand. So if the market will pay for it, that's the price. So we're going to use graphs for the vertex to determine max price. And guess what? At the x-intercepts, what's the y value? 0. Well, the x-intercepts indicate when we make no money, 0. Anything below that graph is a loss in money. Anything above the x-intercept is a profit on the y-axis. And of course, the vertex will represent the max profit. So this is used in business a lot. It's also used in engineering a lot to figure out the maximum stress a material can handle. It's used in, you're going to use the sine curve a lot in electricity, in electrical engineering. So these things actually do have applications, why we're learning them. But this is a completing the square function. Let's go to another case. Let's look at something that looks like this. We're going to change our thing. We're going to find a vertex that is visible. We're going to get rid of this. We're going to see if we can see our graph somewhere. There it is. We're going to multiply this maybe by 6, 7, we'll go 25 maybe. Not quite. 20. Trying to find one with nice even x-intercepts. We're going to go with multiple of 16. We're going to go 64 maybe. Almost there. Well, that's pretty extreme. So we're going to maybe make that something simpler, like 16, 12 maybe 12 will work. Hit the home button. Where are you? You're right there. Almost. Let's do 24. Let's try 24. There we go. 24 is a good one. How do we can see the vertex. It's 3 minus 2. This is a good one for graph. But how do we get there from this? That's the whole point. How do we turn this into the vertex format? Well, this one's a little trickier because we have a number in front. We have a number in front. The 4x squared. So I want you to also keep in mind that our expanded thing over there. There we go. We're going to use this. I'm going to clean it up. There we go. I want you to keep this in mind. This thing in mind. Go like that. Go like that. There we go. A little bit cleaner. Just clean this. Oh, clean this up a bit. There we go. So I know I've got to get to this vertex. I know that's the vertex. We follow the same rules. Move the number aside. This time it's a little bit more complicated. We've got to get rid of this 4 before we half that number. Because I know half this number is minus 12. The opposite is 12. That's not the vertex. The vertex is 3. So clearly I've got to get rid of this 4. Well, we have to factor out. All factoring out, as we open brackets, is we're dividing both of these things by 4. Well, 4x squared divided by 4 is simply x squared. That's why we did it. We wanted this to be x squared with just a 1 in front. By the way, if it was minus 4 in here, maybe I should go back. I'm going to go back and change this to minus 4 to give a better example. Okay, it's the same thing. My vertex is little. Now, just keep it the same. Why make it confusing? Forget it. We'll deal with this. But minus 4 is a possibility. If it was minus 4, I'd have to factor out minus 4 to make this positive 1. But it's not. It's 4. And when I divide this by positive 4 to factor out the 4 out, I get minus 6x. Great. And don't forget our number is hanging out. Well, now I can half it. I can keep the 4 there. Half of minus 6 is minus 3. So that's the perfect square there. That's the perfect square there. And sure enough, look at that. What's the opposite of minus 3? It's positive 3. I got the x value already. I could just plug that positive 3 in here. Positive 3 squared is 9. 9 times 4 is 36. So that comes out as 36. Positive 3 over here times minus 74, minus 24 rather, is minus 72. And then plus 34 over here. Don't forget it. 36 plus 34 is 70. Minus 72 is minus 2. Boom. I got my y value. But let's complete the square. What number would be created if I did x minus 3 times x minus 3? Well, that's where you're using this. It would create x squared. Ignore the 4 in front. We're just focusing on this. X squared. It would create minus 3x minus 3x minus 6x. And so far, that's what we want, right? We want x squared minus 6x. But it also creates a number. It also creates a number, which always ends up being minus 3 times minus 3, or minus 3 squared. It creates a number plus 9. Well, I don't want that plus 9. I don't have a plus 9 over here. So I'm going to have to subtract a plus 9. What's the subtraction of a plus 9? Minus 9. There's one extra trick, though. I don't now just add this number to 34 to figure out my y value. What's minus 9 plus 34? It's plus 23. Well, that's not my y value, so it's not correct. No, to get this 9 out here with this 34, I have to multiply it by this 4. So going back to this, what's the number created here? It's always the square of that, so I have to subtract 9. To get it outside, I have to multiply this 9 by 4. It's minus 36. Now that the 9 is out, I can get rid of it here. I can see I have this here. And now I have minus 36 plus 34. What is that? Minus 2. I've successfully completed the square. So the extra step here is factor out whatever this number is. Whatever this is, half this number. Minus 3. I now have my perfect square. Subtract the square of this number, minus 9, and get it out by multiplying it by whatever this number is, minus 36, and then add the number 2 that we moved aside. Okay. Sometimes you'll see your teacher, instead of moving the plus 34 side, he moves it to the other side of the equation. So he'll have 4x squared here, equaling, instead of plus 34, he makes it equal minus 34 on the other side. He's working solely as if we're at the x-axis. And then he proceeds to do what we did with the perfect square. He factors out the 4, x squared minus 6x. 6x. Then we have to half it. Then we have to half the 6x. We have 4. X minus 3 squared. That's the perfect square right there. Then we have to subtract whatever the square of this is, minus 9. Then we have to get the number out. 4 times minus 9 is minus 36. And it's equal to minus 34 on the other side. Then we add plus 36 to this side. And we get equals to 2. So you'll see sometimes it represented by your teacher like this. And that's because sometimes we'll want to solve, we'll have to find the x-intercepts from completed squares that aren't nice and clean like this. We'll have to be able to solve it. For x-intercepts, you can find the x-intercept from this formula as well. But hang on, this is what we have now. Minus 2 is equal to y. Some of them are even more complicated, though. Some of them, and we'll get to it in a second. And you might say, okay, How would I solve my x-intercepts here? Well, this is our completed square, right? This is our vertex format. X minus 3 squared minus 2 is equal to our y value. What's our y value at the x-intercept? It's 0. It's 0. That's why I say sometimes you'll see the teacher represent it in a different way. Add 2 to both sides, equal to 2. Divide by 4. You have to do outside the bracket first. Divide by 4. You get 2 divided by 4. That's the same as a half. We have to square root it. We have to square root it to get it. Here's a trick with square rooting. Whenever I do a square root, I had to get rid of that square, so I square rooted both sides. There's a positive version, and there's a negative version. Why? Because the square root of 9, for instance, has two answers, 3 and negative 3. That's because if I were to square negative 3, I would still get 9. If I was to square 3, positive 3, I still get 9. So there's always a positive answer and a negative answer when we square root something. So that means x minus 3 is equal to the square root of 2, positive square root of 2, but x minus 3 is also equal to the negative 1 times the square root of a half. Now I can see it's x minus 3, so I just simply add 3 to both sides to get it to the other side. X, square root of x plus 3, and this one is negative square root of x. Sorry, negative square root of half. See that. So notice it says now x is equal to. Well, this is the x-intercept on both sides. Let's find the decimal version to see if we got it right. So square root of a half, we take 1 divided by 2, which is 0.5. We find the square root of it, 0.707. One of these we're going to add 3. We get this value. I'm rounding up, keep in mind. Here's another thing, that square root is exact. The decimal's not exact. And then the other one, the square root that I have, I've got to make negative and then add 3. Because it's negative square root of half. And here's my other x-intercept. That means these should be the x-intercepts on these two graphs, 2.29, 3.7. Let's go see if that's true. Where's the x-intercept? When the graph is at 0. When y is at 0, right? 2.29, 3.701. So you can see the vertex format, when we make it equal to 0, we can find the x-intercepts. And notice it's decimal. Well, we wouldn't have been able to do this through factoring because those decimals are impossible. And what we just did is completing the square, and then we solve for 0. And that's exactly what the quadratic formula is. We'll go into that some other time. But quadratic formula just lets you take the A, B, C values of this graph. In this case, the A is 4, the B is minus 24, and the C is 34. Plug it into a formula. It's really the same thing as completing the square to find the two x-intercepts. And get more into that later. But that's why we're completing the square. That's why we have to learn it. That's why it's important. And to do it, you have to understand various completing the square. There are other situations where the completing the square will be incredibly annoying. Like suppose you have 5x squared minus 2x plus 3. Well, our first step is moving the 3 aside. So we get 5x squared. So as my fingers work. Minus 2x, and I'm going to move the plus 3 aside. Well, my rule is I got to factor out the 5. I got x squared. But to divide minus 2x by 5, it's annoying. It's minus 2 divided by 5. Like that. X. And then that plus 3, we just keep way over here somewhere on the side. So as my fingers work, there we go. Well, that factor I just made, 2 over 5, that makes my life hard. There we go. Remember, I factor out a 5 to do. Well, to find the half of that, whenever you want to find a half of a fraction, here's the solution. You simply multiply the denominator by 2. So that means the perfect square of that is x minus 2 over 10. Okay, there's a 5. That's the perfect square. Notice that's not clean, is it? That means the x-intercept is 1 over 5, or 0.2 for the vertex, 0.2. Now to find the y value, I either can put 0.2 back into the original formula, which is partially completing the square, or I can subtract the square of that. Well, the square of 2 is 4. The square of 10 is 100, so I have to subtract negative 4 over 100. But to get it out, I have to multiply by 5 to get it outside to add to the 3. Well, 5 times negative 4, remember that 5 is just 5 over 1. 5 times negative 4 is negative 20. 1 times 100 is 100. So I get negative 20 over 10, over 100, which is the same as negative 2 over 10. So that's the number once I get it out. Well, I have to add that to 3. Well, I can't add it to 3 because the only way you can add fractions is when the denominator is the same, and 3 the same as 3 over 1, right? 3 is the same as 3 over 1. Well, that means I have to make 3 over 10. The only way to do that is to multiply the top and the bottom by 10. So it becomes minus 2 over 10 plus, what's 3 times 10? 30. What's 1 times 10? 10. Makes sense that 30 over the 10 is the same as 3, because when I take 30 and divide it by 10, I get 3. It's the same. That's just a fractional representation of 3 over 10. Now I can add it. Minus 2 plus 30, 28 over 10 is my y value. So the completed of the square for this is 5 times x minus 2 over 10 squared plus 28 over 10, which is 2.8. Right? That's a complicated completing the square with fractions. That's why sometimes instead we'd use the quadratic equation, because that's going to just be a pain in the butt. But I can now tell you, if I take the opposite of minus 2 over 10, it's plus 2 over 10. And that becomes 0.2. So that's my x value for this vertex. And my value, my y value, 28 over 10 is 2.8. So I'm going to plug this original equation right here, 5x squared minus 2x plus 3, to see if we got it right. 5x squared minus 2x plus 3, I think it was. Let's go back and see if this was what. So 5x squared minus 2x plus 3, and we'll see if we got the vertex. Should be 0.2 comma 0.28. Look at that. We got the vertex. Notice that this graph is above the x-axis. It has no y-intercepts. If I was to solve when y is equal to 0, if I was to use this formula and set it to 0, I would subtract this from both sides. I get minus 28 over 10. I would get rid of this, I have to multiply it by 1 over 5. Cancels out. That's called multiplying by the reciprocal. 1 over 5. I multiply this side by 1 over 5. I get minus 28 over 50. And then I've got to square root it. Well, I'm square rooting a negative number. That tells me right away no x-intercepts exist.